Okay, so here we are in Wolfram, and we're going to look at our lesson. We'll have a lesson and exercises to do. So the lesson is not in high school one, but you'll see it in Wolfram, and in Wolfram we're still in draft version here, but it's going to be lesson 7A, and you'll make a copy of this data representation. Okay, so you'll go ahead and make a copy of it, and I'm going to do the same thing here, and let me make a copy of it. Don't want to rename it, don't want to do any of these things, so all right. I'll go back to the class. Let me go back to the class, and it's just easier to do it this way. Okay, so I'll go back. So I haven't published this, but this is what we're going to do. So we're going to make our own copy. Okay, and so we're going to practice several skills today, and then we're going to do a copy. Okay, and so let's change it into copy here. So we've got our copy of this. All right, and so one of the things that we want to learn about is how do we make data that we can use, right? So a lot of times, if you want to practice, you're not going to actually be collecting from an experiment. And so we know what we can do. We can make a number, right? So make a number 1 to 10. If you wanted 20, you could just make a number 1 to 20. Okay, and that's easy to do. And then something to think about is, well, what if I wanted some extremes? Okay, so what if I wanted 1 to 20 and 81 to 100, right? So I wanted a data set in which everybody either did well on a test, they had in the 80s to 100. Okay, and so then one of the things you can do is, so I've made 2 ranges here, and so as an exercise, I'm going to have you make a list that has 2 separate ranges. So you can use range twice. Okay, so notice what you can do with range. You could say beginning and end, and then if you wanted to do it twice, then you just say, okay, I'll do this 2 separately, and then I'll use join. So I use join to do that. Now notice how join is not showing the new results, so we have to evaluate that again. So I just evaluate again, and now we've got 40 members, 1 to 20 and 81 to 100. So now let's see what our box and whisker chart looks like for list 3. So we go ahead and evaluate that, and we get this box and whisker chart in which we have this fatness, right? So you can see that it's kind of confused by that, right? It's a confusing, and the box and whisker chart doesn't really tell you any much, right? Well, so let's see, could we change things a lot? What if we put a bunch of stuff in the middle? All right, so let's do that. So let's do list 3. So we notice we give that a lowercase l, and we'll say list 3 equals, and then let's just put in 40 values right in the middle. Equals range from, what would you say, how about from 30 to 70, yeah, so 30, comma, 70. So there's list 3. And now let's put list 3 in with our other ones. So we have list 3 here. So now we've got a lot of guys in the data set, and let's reevaluate. Oh, no, I messed that up. Well, no, I guess I didn't. It's okay. So I should have called this list. Okay, so let's call this list 4. So we keep them separate. All right, so evaluate again. So there's list 4, and it's got a whole bunch of guys, but it's got some big little. Okay, so now let's evaluate list 4 and see how that changes. Okay, so now we get a little bit tighter, and let's say that we made, so now let's do this. Let's make list 3, and so you might say, well, what happens if I put even more guys in the middle? And I'll call this list 3A. And I'll do the same thing. So I'll put range equals range (30, 70), and I wonder if I can do it by 0.1. Okay, so what I'm going to say is I want everything, and I want it to be in increments of 1, so there'll be a whole bunch of values. Let's see if that works. Yeah, okay. So now let's add list 3a there as well into our list 4. Okay. So we said, okay, we're going to put all these values in the middle now. Okay. So now list 4 is like that, right? It's got all those things. So now let's reevaluate list 4. And what we're expecting, and what you see there, is now the box and whisker chart shows that the middle half of the values, okay? So think about it as fourths, right? So here's the bottom fourth, the second fourth, the third fourth, okay? So what we've done is we've really made the data be much closer to the center than it was before. Okay. So what did I do there? So look at, I just said, well, I want it between 30 and 70, but instead of going by ones, which is the default value, the default just went 30, 31, 32, I said 30.1, 30.2, 30.3. So I create all this data, real easy to do in it. Now, we're going to learn about mean deviation. So in other words, we find out what the mean is, and then we want to say how far in general from the mean are you. Okay, so before the mean, deviation of list 3 was very far apart. So we'll go back to that, and we'll call that, if we just use list 1 and list 2, right? So let's just use list 1 and list 2. So we'll call this list spread out. So the list spread out equals join, we just join together list 1 and list 2. Okay, so there's the list spread out. Okay, so it's got 1 to 20, and so the mean deviation of, so just start typing list spread out. I think that works. Okay, and I recognize that. So the mean deviation was 40. In other words, the center of that is 50, and on average, they're very far away. They're 40 away. Okay, so now let's look at same thing for mean deviation. So we say mean deviation, but now we've got that list that we made a lot more centered, list 4. List 4. Okay, so list 4, where we put all the values, added over 100 values that were close to the center, which is 50. Okay. And well, let's just see. What if we do? Let's say, what is the mean of list spread out? What's the mean of it? Okay, what's the average of it? Oh, so the average of that is right around 50, right? And what's the mean of list 4, which is okay, so we'll flip in here. Okay, and then say, well, what's the mean of the one that we've added all the stuff to, list 4? Oops, and notice how it didn't like that. Well, it's because I used a capital letter there. So I'll try again. Okay. So the means are very close. So this is, okay, and then you might say, well, I don't like that one, right? So you can do that /n, and it'll change from a fraction to a decimal. Okay, so you see the means are essentially very similar, but the deviation, how far on average are you from the mean, is much greater. Okay. So now let's look at standard deviation, and that is one of our goals, is to have you looking at these differences between mean deviation and standard deviation. Okay. And so we say, okay, there we've got it, list 4, standard deviation. And now let's look at the standard deviation of list spread out. Okay. So we're going to say standard deviation of list spread out. Okay. And we get that, and you can see that the standard deviation, as if you've read about it, involves the square root. But we don't really care how it got there. Okay. Okay, so you say, oh, look at, we have this much greater standard deviation. So the list spread out has a standard deviation of 40, whereas the mean so now we want to say, well, what's the mean deviation of the list spread out? So we put in mean deviation. Hey there, hi Roger. And so we're going to compare those two. And what we expect to find is that the standard deviation accentuates slightly more the differences when it's greater. So that isn't really such a big difference, so I was a little surprised by that. All right, so now let's look, and so what if we want to have just a bunch of the same numbers? So one way to do it is just to say random integer, and then just say, give us a range from 5 to 5, okay? And so there is another way, right? That seems kind of like a clunky way to do it. So you can do this as well. So you can say table, okay, and I just want, say 5, comma, and then you could say how much do you want to do that? 1, comma, 10. Okay, so I want 10 5s. Let's see if that works. Okay, so that doesn't seem to work, right? And so it doesn't like that as an iterator. Let's see if I put I in there and say, yeah. Okay, so you don't use the variable except to say do this 10 times. So this is another way you could do it if you like that better than saying random in. But you see what we do here is we say I want a table of 8s and 12s. Okay. Well, what's the mean of that? Right, so we've got a table of 8s and 12. So I say mean list average of 8s and 12s. Okay, so what's the average of that? Okay, is 10. Okay, and how far are we from there? We are 2 away. Okay, what's the standard deviation of our list average 8s and 12s? Okay, so it is. So then we say, all right, so we just do this one, and now we say, okay, well, I can't really compare those very easily, so I'm going to put in standard deviation, and then that / n, and I get it's 2.05. So in other words, the standard deviation and mean deviation on that have hardly any changes at all. But what if we change? We're going to change this list, right? So we're going to say what's going to happen if we have the new list has instead of all 8s, it has 7s and 9s and 11s and 13s. Okay? So it has that. So when we look at the mean, and it's our list average of 7s, 9s, 12s, 13s, well, we expect the mean to be the same, right? The mean, the average is still 10. Right? And if we do the mean deviation, for that, we also still get 2. Okay? So what we did is we substituted instead of 8s, 7s and 9s. So from the point of view of mean deviation, it's the same, right? So it used to be everything was 2 from the mean, and now some are 1 and some are 3. Still, the average of how far you are from that mean of 10 is 2. But what about standard deviation? So the standard deviation says you give more importance to things that are further away because you square and then take the square root. And you can see that you get a significant difference. So the standard deviation says, oh no, you've got bigger variance. And you can see that this is what we're trying to get to, is this idea that those 3's are counted more than the 1's in standard deviation. In mean deviation, when you put a 3 together, the 3 away and 1 away. So when you put a 7 and 9 together, all together, they're 4 away from the mean of 10, and so the average was 2. In standard deviation, you took the 3 away and squared it, 9. The 1 away, squared it, 1. They were 10 away, and then you take the square root of that, and you get square root of 10, which is a little bit over 3, and so that made a bigger thing. Okay. Next, we want to look at making a table with ordered pairs. Okay, so you could just say I want 10 1s and 2s. Or you could make kind of a random one where you say, okay, I want to have a table that has these ordered pairs between 1 and 10 and 1 and 100. Okay, and so I'm going to call that hours studied and test score. So people studied between 0 and 10 hours, and they got scores between 0 and 100. And so let's do a list plot of that. Okay, so we're going to do list hours studied test score. Okay, and it seems to like that. So we say, okay, what does that look like? And you can see this pattern of on the x-axis, how many hours did I study, and then what score did I get? And so we're going to look at that, and the idea is there a relationship between hours studied and test score? And here, in this next one, you see the idea that you can create, so that was just completely random, and then from the book that we've been using, it says let's try something else. So let's try a table, and it's going to have 20 values. Okay, it's going to have 1 through 20. Okay, that I 1 through 20, but then the value that goes with it, we double I, and then we do random real either -2 or 2. So what this is going to do is, if we didn't have the random real, what if we didn't have that? Okay, so if we go through here, and we're gonna take that out. Okay, so we take that out. Okay, and look what happens. So we get just what you'd expect. Okay, so we double everything, and if we plot that, look, we get this perfect relationship. So this is what we're trying to learn, is that in math you can get this perfect relationship, right? But if you were to study something where you have a relationship and measure it in the real world, you don't get that. And that's what this is trying to simulate, is saying, oh, well, it's close to double, right? So for example, I put in an hour effort and my score went up almost double the points of the hour. But in fact, it varies a little bit, and that's what this random real does. So we look at this and we say, okay, so it's going to be double, but then maybe a little more, a little less. And so now we go back and see, well, that's what happened. And we'll list our plot. Okay, and so this is the idea we're going to use for the next few weeks, is that when you go to data, you're going to find that it's close to a function. So it's close to, for example, y equals 2x. But it doesn't quite fit. But we want to make something we want to say, well, what's the closest function that would fit? Okay? And this is called, this kind of line is a positive correlation, right? Is that as our number goes up here, so it might be hours studied, our points go up. And so now we're just going to look at a way to define a function. So let's try and define a function y equals 3x. So we're going to do a plot of 3 times x. And so here's our plot here, right? And you could change that, right? So you can make it steeper if you wanted. You could say y equals 4x, right? And you could make a steeper plot if you wanted to. And so then we just define a function. So we're going to define a function f. And so that's what we've done here. We've defined a function f. And you see how there's no output. It's because we've just created this definition of f. And now we can put in anything we want. So we can say f of 4. Okay. And so the author just says, well, imagine that you just have a simple thing where you have objects where the width is 3 times the length. Okay? So you say, okay, well, what if I find out the length is 4? Okay, what do I do? And then they say, okay, I'll put in a 5. What do I get? Okay, so a real simple idea, right? So that's what he's showing here. Is that okay? So we could have this simple function that just triples whatever the input is and comes out. And so then what he says is, well, can we plot this? And here's an interesting one, right? We say, okay, well, we plot it, and then in particular we look and we put a line on the plot there. Okay, and well, what if you had something that? So what else would be a line on? So you could say, okay, well, what about in particular 412? Where is that? And then maybe you came along and said, well, I think 512's on that line. He said, no, it's not on that line. Okay, it's close, but it's not on that line. Okay. But what they're saying is, here's this perfect correlation, right? Is that there's this direct relationship between x and y. Y is 3 times x. And so then he says, well, let's put in some experimental values. So here's our experimental values, and you can see they're kind of close, but they're not exactly that. And that's where we're going over the next few weeks. Is we get some values, right? So we say we're going to test everybody. You're going to sleep longer, and we're going to see if your test score are up. Or you're going to drink our magic potion, okay? And so based on how many ounces of magic potion, how much did your score go up? And we're going to take a measurement. And so now, this is similar to what we'll do. Is we're going to take a set of data and try and get a line that is close to matching the data. You can see it's not going to be perfect, right? And that's the thing that you're trying to understand in these next few lessons, is that your measurements are going to be real world measurements won't fit perfectly on the line, but you can get a line perhaps that is close to it, and that helps us to predict in between what happens, or to predict what happens outside. And so this one would predict. So we put in, oh, well, if we put a 1.1 in, we should get out 3.3. All right. So now if we look at what we said, so we just did this random thing. We said, okay, make something between 1 and 10 and something between 0 and 100. And you can see that if you just do it, if we just say random, because we said just put random numbers in, there is no line that fits here. So there isn't a correlation based on that data between the hours that you studied and your test score. Okay. And so I was having a little trouble here. So this was an interesting one for me, is why didn't anything show up here? Okay, and then I finally understood, so when I look at this, is that it was plotting everything, it just didn't show it, right? So now when you do it, see, oh, suddenly there's points there. It's because I didn't have enough, I didn't line plot enough. And so then if I reversed it, you see what happened, right? Is that I put in plot second, and then it said, oh, you want to show the range up to 100, and then there's a line, and you can see the line doesn't work very well, right? And so if you were going to make a plot, you might say, well, I think it's a little bit closer to 5x. Let's see if that line works better. Oh, not even close, right? And so you say, oh, maybe it's 9x. Okay, so maybe 9x fits better. And then you might say, well, actually, maybe it's instead of being a direct relation, maybe there's a constant that we add in. And so now you see that we say, oh, maybe it's like there's this base score of 60. Okay, so think in terms of how much you studied. Well, maybe even if you don't study, you get a 60. And then based on the hours you get of study, you add to your score. And that is what usually happens in things that you're looking at, is that it's just like in Math 1, y equals mx plus b, is you try and get the points, and the points will match up most closely to something that has that form, y equals mx plus b, if there is indeed a correlation. Okay? And that's what we're going to be working on in the next few weeks. And so the exercises will give you some more practice in this.